Welcome back, everyone. I am so glad you're joining us today because we're going to be diving into something that is literally all around you right now. It's shaping our entire universe as we speak. We're talking about the electromagnetic spectrum. Now, you can kind of think of this as a huge invisible family of waves. From the light that's bouncing off whatever screen you're watching this on to the invisible signals keeping your phone connected, they are all part of this exact same family.
And just like any family, they share some pretty deep-rooted traits. Think about this absolutely massive number. 299,792,458 meters per second. We usually just round that up and call it the speed of light, which is about 300,000 kilometers per second. But here's the really crucial thing to understand. That isn't just the speed limit for the light we can see. This is the exact universal speed limit for every single electromagnetic wave when it's traveling through a vacuum, like space.
Okay, here's our roadmap for today. We're going to cover the essential properties of waves, the wave equation, origins in the atom, the electromagnetic spectrum, real-world applications, and finally, the danger of radiation. Let's jump right in.
Section 1. Essential properties of waves, the family traits.
So even though these waves look and act totally differently in our day-to-day lives, the whole family plays by a strict set of rules. First up, they are all a form of radiation. That just means they spread out from a source. And they don't need a physical medium to travel through either. They can zip right through the empty vacuum of space at that crazy speed of 300,000 kilometers per second. But here's where it gets really fascinating. They are what we call transverse waves. This means their oscillations or their vibrations happen at perfect right angles to the direction the wave is actually moving. And if you're wondering what exactly is vibrating, it's not physical matter at all. It's actually electric and magnetic fields oscillating. And as they do this, they transfer energy. The source loses energy when it sends the waves out, and whatever absorbs them gains that energy.
Section 2. The wave equation, the mathematical rule of inverse.
This rule is just a brilliant example of how the universe balances the scales. The wave equation simply states that a wave's speed equals its frequency multiplied by its wavelength. So what does this actually mean for us? Well, because the speed of electromagnetic waves in a vacuum is always locked at that constant 300,000 kilometers per second, the other two variables are stuck in a strict seesaw relationship. If you crank up the frequency, so more waves are passing by every second, you absolutely guarantee that the wavelength has to decrease, and it works the other way too. If the wave gets longer, the frequency drops. They are perfectly, inversely proportional.
Section 3. Origins in the atom, where waves are born.
All right, before we check out all the different types of waves this equation creates, we really need to ask, where do they actually come from? Well, it all starts with the atom. You've got this central, positively charged nucleus, and it's surrounded by orbiting, negatively charged electrons. Every piece of matter in the universe is built out of these atoms. The universal rule here is that electromagnetic waves are emitted whenever charged particles oscillate or lose energy. So think about an electric current flowing through a wire. That's basically just free electrons moving around. If you force those electrons to oscillate, boom, they emit radio waves. Or take an old-school glowing light bulb. The atoms in that super hot filament are vibrating frantically, and because of that intense vibration, they emit infrared and visible light. And going back to our equation, the higher the frequency of that atomic oscillation or the bigger the energy jump, the shorter the wavelength of the wave it shoots out.
Section 4. The electromagnetic spectrum, the full range.
To really wrap our heads around the massive scale of this wave family, let's just look at the two extreme ends. On the absolute lowest energy side, we have radio waves. A single one of these waves can literally stretch for several kilometers. But then, on the complete opposite end of the spectrum, you have gamma rays. Their wavelengths are so incredibly tightly compressed that a single wave is less than 1/1000th of a millimeter long. I know, it's kind of hard to even picture that, right? But that tiny microscopic wave and that massive kilometers-long wave are fundamentally the exact same physics. They are just operating at drastically different frequencies.
Section 5. Real-world applications, traveling the spectrum.
Okay, so how do we actually put this vast spectrum to use? While starting down at the bottom with radio waves and microwaves, these are pretty much everywhere in our daily routines. Long-wave and medium-wave radio signals give us all our AM and FM broadcasts. Then, as we step up the frequency just a little bit, we enter microwave territory. This is the absolute backbone of modern connectivity. This specific band is what makes your smartphone work. It connects our satellites, it runs your home Wi-Fi, and powers radar systems. And yeah, of course, it's also responsible for the specific heating effect that we use to warm up leftovers in our kitchen microwaves.
As we keep climbing up the frequency ladder, the waves get shorter, and we hit the infrared band. Now, basically, anything that is hot is giving off infrared radiation. We intentionally harness this part of the spectrum for things like radiant heaters to keep us warm, but it's also used for security alarms, the tiny pulses of light that carry our internet data through underwater optical fibers, and even just the simple, invisible signal coming from your TV remote. Right above infrared is this incredibly narrow, tiny sliver of the whole spectrum. It's so small, but it essentially dominates our entire human experience. I'm talking about visible light. Emitted mostly by the sun, this is literally the only type of electromagnetic radiation that our human eyes have evolved to actually see. But if you step just a hair past visible violet light, you hit ultraviolet, or UV, and this is where the energy starts getting pretty intense. UV light is what gives you a suntan at the beach, but it's also what can cause skin cancer and eye damage if you're not careful. On the more practical side, though, we can use that high energy to kill bacteria. And it's also what causes fluorescence, making certain chemicals glow super brightly in the dark.
Moving even higher, we are now entering the realm of very high frequencies and extremely short wavelengths. X-rays carry so much raw energy that they can actually pass right through soft, dense materials, like human tissue, but they get blocked by harder materials, like bone, which is exactly why they're the ultimate tool for medical imaging. And it's pretty interesting, while getting hit with excessive X-rays can unfortunately cause cancer, we can also highly target those exact same X-rays to destroy cancer cells in medical treatments.
Section 6. The danger of radiation. High-frequency hazards.
As we arrive at the absolute peak of the spectrum, the utility is still there, but the physical risks absolutely skyrocket. At the highest frequencies and the shortest wavelengths possible, we find gamma rays. These guys are emitted purely by radioactive materials, and they come with an extreme radiation danger warning. Because their frequency is just so insanely high, their energy is staggering. They can very easily slice through and damage living cells and DNA. But, human ingenuity is pretty amazing. We've actually found ways to safely use this dangerous extreme. We harness gamma rays specifically because they're so lethal to living organisms, using them in tightly controlled environments to perfectly sterilize medical equipment and even food packaging.
And that brings us to the end of our journey across the electromagnetic spectrum. From those gentle, kilometers-long radio waves bringing music to your car, all the way up to microscopic super high-energy gamma rays inside a nuclear reactor, it's all just oscillating electric and magnetic fields obeying the exact same universal speed limit. So, I want to leave you with this one thought to ponder. If all these waves are just invisible energy fields zooming around at 300,000 kilometers per second, what invisible energies are passing straight through the room you're sitting in right at this very moment? Wi-Fi? Radio stations? Infrared heat from your own body? The universe is incredibly busy, even when you can't see it. Thank you so much for exploring this with me today. Keep asking questions, and I'll catch you in the next explainer.